I'll briefly demonstrate how to use an interactive simulation that uses the Peng-Robinson equation of state for a binary mixture in order to plot isotherms, and the mixture is normal butane, normal octane. Important to notice that the results that we obtain are plotted on a log pressure, log volume diagram. The simulation's on the LearnChemE site, and here's a link to the simulations. Let's look at what we are plotting. So we have two curves. The blue curve corresponds to the liquid phase. So we specify the liquid mole fraction with this slider. And then this is the isotherm. So we specified the temperature 389 Kelvin. If we change the temperature, we change the isotherm. We've used, in this case, Raoult's law to calculate the vapor composition. This is pretty close to ideal system of normal butane and normal octane. We could certainly use the equation of state and set if your gas is equal to two phases, we're going to get very similar results. It's much easier in this simulation just to use Raoult's law to demonstrate the concepts. And so then the liquid composition on the blue curve is in equilibrium with the vapor composition on the green curve. And of course, they have different compositions because they have different saturation pressures for the two components. So let's look at this simulation of what happened and look at how things change if we change temperature and the liquid mole fraction. So here's the simulation. If we change the temperature, then both these curves are going to change. And if we change the mole fraction, we're changing liquid phase mole fraction, so that changes what this curve looks like because it's a different composition. And then correspondingly, it means we plot a new vapor phase composition curve, isotherm, that corresponds to the vapor phase that's in equilibrium. So you can see as we change one, we change the other. And so the idea here is that we can use the equation of state to better understand behavior for a non-ideal vapor phase, for example. And we've used Raoult's law in this case because we're at relatively low pressures and pretty good approximation. In these simulations, we have details of the equations here and also directions corresponding to the things I just described.